Today we shall see the selection rules for IR spectroscopy. The molecule will absorb suitable radiation when its natural frequency of vibration matches with the frequency of incident radiation. That means the energy is absorbed by the molecule followed by change in the amplitude of molecular vibration. The second rule is a molecule will absorb IR radiation if there is a change in the vibrational state associated with the change in the dipole moment of the molecule. The dipole moment arises from the separation of charge within a molecule. That is, dipole moment equal to magnitude of the charge and the vector change. In case of hydrogen chloride, it is made up of two atoms, hydrogen and chlorine. Among them, the chlorine is more electronegative than the hydrogen. So therefore, the electron charge density is shifted towards the chlorine atom. Hence, it creates an electric dipole. So the absorption of IR radiation will bring about the change in the dipole moment. Hence, the molecule is said to be IR active. And the third selection rule is if the vibrational quantum number changes by unity, then the IR radiation is absorbed by the molecule. In case of the polyatomic molecules, the non-linear molecule can have 3n minus 6 different types of vibrations where n is the number of atoms, and for a linear molecule it is 3n minus 5. The intensity of the absorption band is affected by two factors, whether the vibration is stretching type or bending type. Usually, the stretching will change the dipole moment to a greater extent than the bending. Hence, whether it is bending or whether it is stretching or bending, if it is followed by the change in the dipole moment, then the light is absorbed by the molecule. And if the change in the dipole moment is more, then more intense is the IR band. Greater the difference in the electronegativity between the atoms involved, then larger is the dipole moment, hence larger is the peak. So in case of IR spectrum, for the sake of convenience of study, it has been divided into two main regions called as functional group region and fingerprint region. The functional group region is from 4000 per centimeter to 1600, and from 1600 to 400 per centimeter is called as fingerprint region. And again, in functional group region, it is classified into three headings. The first part corresponds to the OH, NH and CH stretching bands. The next region corresponds to the triple bond region, and from 2000 to 1600 is known as the double bond region. Here are some typical spectra corresponding to N-pentane, where the sharp peak here corresponds to the CH stretching. So the CH stretching is found to be around 2850 to 2960 per centimeter. Similarly, in case of butanol, The OH stretching vibration is occurring at 3200 to 3640 per centimeter, followed by a broad peak showing the hydrogen bond formation. In case of butanone, a typical ketone, the carbonyl group appears at around 1700 with a sharp peak. So in this way, the peak values are very useful in assigning the nature of the bonds present in a molecule. And along with these prominent peaks, there are also small peaks corresponding to various types of the bonds present in a molecule. In case of alkenes, the C double bond C stretching band occurs around 1620 to 1680 and CH bond around 3000. Similarly, in case of alkynes, the C triple bond C bond occurs around 2100 to 2260 per centimeter. Similarly, the CH bond arises at around 3000 per centimeter. So with this chart, it is possible to assign the peak wave number in case of different kinds of bonds. The CH bond in case of saturated alkanes will occur around 3000 to 2850. Then the CH bond in case of sp2 hybridization, that is alkenes, will be having slightly higher value than the single bond. Similarly, triple bond carbon with hydrogen occurs at 3300. That means as the hybridization changes here from sp3 to sp2 to sp, there is a increase in the s character, hence the bond length decreases. That is why the stretching frequency will increase. Similarly, in case of OH, the free OH without any hydrogen bond formation occurs as a sharp peak around 3600, but when the hydrogen bond formation happens, there is a weakening of OH bond, and that is why the peak frequency decreases. And in case of NH, the stretching frequency for primary amines will occur around 3450 to 3100. As you can see here, out of oxygen and nitrogen, oxygen is more electronegative than nitrogen, hence the bond length here increases. That's why the peak frequency will change. So here you can see the stretching frequency for carbonyl groups in case of various types of the compounds. Among them, we can see for aldehydes and ketones, it is around 1740 to 1665. So if there is a peak around this region, you can say that any of these compounds with carbonyl group may be present. Hence, the carbonyl compounds typically are characterized by the presence of peak around 1700. So, the carbon to carbon triple bond in alkynes will occur at 2260 to 2120 per centimeter. Then, in case of the halogens with chlorine, bromine, and iodine, So you can see here, as the atomic mass increases, the peak value is decreasing. Usually, the stretching frequency will occur at higher values than the bending vibration because more amount of energy is required for stretching than the bending. So the factors influencing group frequencies. It depends on the bond strength and the reduced mass. So in general, energy required for excitation increases by decreasing the atomic mass. So when there is a decrease in the atomic mass, the energy required for excitation will increase. That means you can see here, for the atoms which are attached to carbon atom, that is CH, C double bond C, CO, Cl, Cbr and Ci. The atomic mass of these atoms which are attached to carbon is in the increasing order, and hence the peak value is decreasing. Similarly, in case of the bond strength, as the bond strength increases, the energy required for the excitation will increase, hence the peak value also increases. Hence, the frequency depends upon the bond strength and reduced mass. As the atomic mass increases, there is a decrease in the peak value. As the strength of the bond increases, there is an increase in the peak value. Then inductive effect and the mesomeric effect. In case of OH stretching frequency, methyl alcohol, phenol and the acetic acid. So here you can see the OH stretching bond frequency is decreasing in this order. This is because in case of phenol, there is a mesomeric effect which will hold the hydrogen atom to a greater extent than in the methanol. Hence, the OH frequency will decrease and conjugation will lower the frequency of absorption. In cyclic compounds, if the bond angle is reduced below normal, that is 120, leading to more S character in the bond, hence it is shortened and there is a increase in the wave number. So as the bond angle decreases, the more strain is developed, hence more energy is required to excite the vibrational energy levels. Then in case of hybridization, as the hybridization in case of sp2 and sp3, the sp3 hybridized carbon atom will occur at lower frequency than the sp hybridized carbon atom. More the S character, stronger is the bond, hence absorption is at high frequency. Then effect of hydrogen bonding. In general, the hydrogen bonding shifts the frequency of absorption to lower wave number because as there is a formation of hydrogen bond, the bond gets weakened, hence there is a shift in the frequency of absorption to lower wave number. You can also see whether it is intramolecular or intermolecular hydrogen bonding in case of the different molecules. So the inter and intramolecular hydrogen bonding can be distinguished by dilution. In case of intramolecular hydrogen bonding, it is independent of the concentration because it is the internal effect. Hence, intramolecular hydrogen bonds remain unaffected on dilution, so the absorption band also remains unaffected, giving the peak at same position in the IR spectra. But in case of intermolecular hydrogen bonding, the it depends on the dilution. As there is a more and more dilute, that is at lower concentration, there is a decrease in the OH stretching frequency. That means it is possible to decide whether it has in intermolecular hydrogen bond or intramolecular hydrogen bond depending on the dilution and by studying the IR spectra. So the different applications of IR spectra is it is possible to study the progress of the reaction. So during the reaction there is a change in the bond length and it can be visualized by taking the IR spectra. And it is possible to study the purity of the compound. That is, if the compound is impure, it reduces the sharpness of the individual bands, and if it is pure, then we will get a sharp peaks. Then the shape of the molecule can be assigned by means of the IR spectra. And it is possible to study the organometallic compounds also by making use of the IR spectra. The absorption frequencies for different molecules will give us an idea regarding the nature of the metal ions present in a molecule. Then it is possible to detect the functional groups. As I told you, depending on the functional groups, there is a characteristic peak which appears in the IR spectra. So by assigning the values, it is possible to study the nature of the molecules. So in case of alkanes, the CH bond is saturated and it occurs at around 2800 to 2960 per centimeter. Hence, the compounds, if they have saturated CH bond, then they will show peak around this value. So here is a table which gives you an idea regarding the stretching frequency for different types of functional groups. Among them, the one which is important is the CH stretching frequency, then OH, then for NH, maybe it is for amines or amides, it occurs slightly at higher value than the OH stretching frequency, that is 3300 to 3500. But in case of OH, for alcohols, it is around 3500 to 3600. Then in case of carboxylic acids with OH bond, it is 3500 to 3650. Then if there is a hydrogen bonding, then slightly it lowers along with the formation of broad peak. So these are some of the applications of IR spectra, and it is now an indispensable part of the research field, and especially in medical field, pharmaceutics, forensics, polymers, food, everywhere, to study the nature of the bonds, to study the nature of the molecules. IR spectra is definitely a tool which is used in elucidating the structure of the molecule. Thank you, and this completes the topic on IR spectra. If you have any doubts, you can clarify it in the class.